In this lecture, we'll learn how to use conditional instructions in programs and also learn how to create code for loops in RISC-V. Let's first recall the branch instructions. A branch instruction will jump or branch to the target of the branch, which is an instruction that contains a label identical to the label that appears in the branch instruction, if the condition that is testing is true. If the condition is false, the execution will continue in the instruction that comes immediately after the branch. An example, a branch equal instruction will jump to the target L1 if RS1 is equal to RS2, otherwise it will execute the instruction that comes immediately after the branch instruction. A variant of that is the branch not equal instruction that will test whether the two values are not equal and will go to the target of the branch if the values of the two registers is not the same. And a unconditional jump instruction will use the JAL instruction, that's the jump and link instruction, specifying the register 0 to the jump and link instruction, because the jump and link instruction will compute the value of PC plus 4 and write that value in the register specified in the instruction. If we specify register 0, that write will take no effect because it's impossible to write into register 0. And what we have, the effect is of an unconditional jump instruction. Here is a simple loop code in C. It's a while loop. This while loop will be reading the position I of an array called save, and will be testing whether that position is equal k. And as long as it's finding elements in save that are equal k, it will keep increasing the value of the index by a value j. It's in a variable j. In order to write the assembly code for this while loop, we need to have some assumptions about where each one of the variables are. In this example, I is in register S3, J is in register S4, K in register S5. The base of the array save is in register S6. Remember that the base of an array is the address of the element 0 of the array, and save is an array of 4-byte integers. In order to create the assembly code for this loop, we need to obtain the memory position that contains the element save plus save sub I. We need to obtain the value that's in that memory position and put it into a temporary register. Let's say that we put it into T0. Then we will test to see if the value that we just got from memory is different from the value k. If the value is different, we'll go to the exit or to an instruction that has the exit label in front of it. Again, notice that the condition that I'm testing in this example is whether save I is different from k, because I want to know whether it's time for me to go to the exit. Otherwise, if they are equal, I will increment I with the value of j, and then I need to go to the loop to do it again. In order to load the value of save I from memory, I need to compute the address of the position save I. And to compute that position, I need to multiply I by 4, and then add the result of that multiplication to the base of the array save, which is in S6. That gives me the address of the position I of the array save. I now will load from this address by using a load word with an offset of 0. And then I will encode my branch not equal condition, where I'm going to go to some instruction that contains the label exit in front of it. Next, I will add to S3 the value of S4 and S3, and then I will jump to the loop with an unconditional jump. My exit instruction will be somewhere down there. That's where the two paths will rejoin. And my loop label is up here, where I started the computation of the address for the next position of the array. So this is a perfectly fine code in RISC-V. We'll run and we'll execute the code that is specified in the while loop. Now, the question is, how can I improve this code? Let's take a look at what the code is doing. The code is loading the value of save I. We're going to use a flow diagram to understand the code. Then the code is asking whether the value of save I and k are different. So it's a test. And if they are not different, so if the answer is no, then the code is adding j to I and going to the loop. So the go to the loop is the jump in conditional instruction. If the condition save I different than k is true, so if the answer is yes, then I go to the exit. So this is the code that I have right now. I'll propose a transformation to this code. The transformation to this code will consist in doing the same that we do in the original code. I'll load the value of save I, and then I'm gonna ask whether save I is different than k, just like I did before. If the answer is no, I'll increment j and I. So far we are doing exactly what we were doing in the original code before the transformation. But now, instead of the jump to the beginning of the loop, I will have instructions to do load save I again. And now I will test whether save I is equal k. If the answer is no, I go to the exit. If the answer is yes, I go back to the position where I had incremented the value of I. So what I have done here is I have done an initial load and an initial test. And then I repeat, and then I got the body of the loop, and then I repeat the load and the test, but my second test is different than the first one. So, and if the answer was yes for that first test, I would be going to the exit. So the code that I have here now is a load save I, like I had before. I need those 3 instructions. Then I have the branch not equal, like before. And then I have the addition of I plus j, like before. And now I have those 3 instructions that load save I appearing again in my code. And then I have my conditional test at the end of the loop now. That is, the conditional is now asking whether I need to do the loop again. That's why the condition now is a branch equal. If it's equal, I need to do the loop again. And now my loop label does not go to the top of the code. It goes to the place where I incremented I and j, which is the instruction add s3, s3, s4. And if no, I go to the exit. If yes, I go to the exit. So this is the code after the transformation. This was my code before the transformation. If I look at those 2 pieces of code, it looks like that after the transformation, my code is longer. Looks like it would be worse to have the code that I have after the transformation. However, let's take a closer look, and let's imagine that this loop executes at least 1,000,000 times, if not more. So if the loop executes 1,000,000 times, the instructions that are inside the loop will be executed 1,000,000 times. And any instruction that's outside of the loop, we're going to execute 1 time in this example. So if I draw a line around the instructions that are in the loop, I'll see that before the transformation, I had 6 instructions inside of the loop. And after the transformation, I have 5 instructions inside of the loop. I got rid of the jump and link instruction that appeared in the code before transformation. And I could have saved 1,000,000 instruction execution. So this kind of thinking and this kind of transformation is what assembly programmers and compilers do in order to improve the performance of the program. There are other conditional operations that I have in RISC-V. There is an operation that does not do a branch or a jump. It simply sets the value of a register to according to a condition. So this, for example, is the set less than operation. It will gonna set the operation would be if RS1 is less than RS2, then the destination register receives the value of 1. Otherwise, the destination register receives the value of 0. So it's set less than because the destination value, the destination register is set if the condition is true. I can also have a set less than immediate, where I am comparing the value of a source register with an immediate value, with a constant. So if the value in the source register is less than the immediate value, I set the destination, otherwise I don't. I can use this set less than operation in combination with a branch equal instruction or with a branch not equal instruction. So for example, the top set less than will set the value of t0 if s1 is less or equal. So if s1, if s2 is less than s1, then I will branch now if t0 is 0. So if s1 is less or equal than s2, then I'm going to be branching to s1. So this is equivalent to the instruction branch less or equal than. I can also have a branch on less than. So if rs1 is less than rs2, I'll be going to the target of the branch. Otherwise, I execute the next instruction. I have a branch on greater than or equal to. So in the previous slide, I saw that I have a branch less than and a branch greater or equal than. Should I have a branch greater than and a branch less or equal than? So do I need a BLT and a BGE? The answer is no. If I want to have the register S1 and S2, how do I branch on S1 less than S2? All I need to do, how do I branch on S1 less than or equal to S2? All I have to do is to ask whether S2 is greater or equal than S1. So all I need to do is to flip the order of the registers. And the same thing, if I wanted to do a branch on S1 greater than S2, I can do a branch on S2 less than S1. So by changing the order of the registers, I obtain the other two branches, and I don't need to have them in the instruction set of the processor. There are other branches that are pseudo instructions. A pseudo instruction is an instruction that does not really exist in the processor, but that the simulator will give to you. So for example, I have a branch equals 0. So I just need to provide one source register, S1. So if S1 is equal 0, I'm going to be branching to the target at 1. So it's testing whether S1 is equal 0, and the simulator will transform that instruction into the instruction branch equal S1 0 L1. So you can write that instruction in either way. We also have a branch not equal 0, and that is implemented as a branch not equal S1 0. We have set less than and set less than immediate that are the signed versions of these instructions. So if I have the instruction set less than S0, S1, T0, what will going to happen is that T0 will be equal 1 if S0 is less than S1. But there are also unsigned versions of these instructions. So for example, if I have a set less than unsigned, the unsigned version of that instruction. So let's consider what happens if S0 happens to have all the bits equal 1 and S1 has the value 1. So if I interpret these values as signed numbers, so two complement numbers, what will going to happen is that S0 is the value minus 1 and S1 is the value plus 1. And I'm saying that I need to set the value of T0 if S0 is less than S1, and it's true minus 1 is less than plus 1. If I use the unsigned version of this operation, S0 will be interpreted as an unsigned integer. So this will be a very, very large number. And in this case, T0 will receive the value 0. The last concept that we want to study in this class is a very important concept both in compilers and for understanding programs. Is the concept of a basic block. It is also a very simple concept. The idea of a basic block is that a basic block is a sequence of instructions in your program, but there are some constraints that we impose in this sequence for it to be a basic block. So if I have the instructions in my program, one coming after other, one of the constraints that I have is that a basic block has no branch targets inside the basic block. The only place in the basic block that can be the target of a branch is the first instruction in the basic block. So I can jump. I was coming along with my instructions, and where I change the color here is in the instruction that will be the first instruction of the basic block. Then there will be several other instructions potentially in the basic block. No instruction inside the basic block can be the target of a branch or a jump. And no instruction inside of the basic block can be a branch or a jump. It only can have a branch or a jump at the end of the basic block. So this concept is very important because all the instructions inside a basic block must be executed together in sequence. And one way to think of the basic block is if one of the instructions inside the basic block is executed, then you know that all the instructions must be executed because it's impossible to jump to the middle of the basic block and it's impossible to jump out from the middle of the basic block. It can only jump out in the end. So compilers will identify basic blocks. You can always break down an assembly program in its basic blocks, and then you can reason in terms of the basic block. I'm introducing this concept here because it may be much easier to debug your program if you think in terms of basic blocks. So let's do a recap of what we learned in this lesson. We learned that there are several different types of branches in the processor. Some of them are actual instructions in the RISC-V, and a few of them are pseudo instructions that get converted into the instructions that exist in the processor. We learned that there is a set less than instruction with different variations. Some are signed and some are unsigned, that we can use simply to set the value of a register according to a condition. We have learned how to write the code of a loop, and we have also learned that when we do write the code of a loop, we can transform the loop in order to optimize the code. And we have learned the important concept of a basic block. And this is what I had for this lesson.